the most dangerous galaxies ever discovered. Space is not the serene, quiet place we often imagine. It is a boiling cauldron of energy, where stars are born and die, where black holes tear apart space-time, and where galaxies collide with forces that surpass any earthly concept of catastrophe. Among the billions of galaxies scattered across the visible universe, there exist those that can truly be called dangerous, not in the sense of posing an immediate threat to Earth, located trillions of kilometers away from them, but dangerous in their capacity to destroy planets, star systems, and even other galaxies. These are cosmic monsters that rewrite the rules of physics in their vicinity, and remind us how fragile life is in the universe. When we gaze at the night sky, we see calm points of light twinkling through Earth's atmosphere. But behind each of these points lies an entire world, and behind some, entire galaxies containing hundreds of billions of stars. Most of these galaxies lead relatively peaceful existences, slowly rotating through cosmic emptiness, their stars born and dying in predictable cycles. But there are others, galaxies that seem to have gone mad, ejecting unimaginable amounts of energy, tearing apart surrounding space with their gravitational fields, emitting deadly radiation across distances of thousands of light years. These galaxies are true titans of destruction, and studying them helps us understand not only the structure of the universe but also what threats could potentially await any civilization daring enough to explore the cosmos. Let us begin our journey with one of the most fascinating and frightening categories of dangerous galaxies: active galactic nuclei. These objects are supermassive black holes located at the centers of galaxies that consume matter at such speeds and in such quantities that the process is accompanied by energy output exceeding the luminosity of all the stars in the galaxy combined. Imagine a black hole with a mass of millions or even billions of suns, around which rotates an accretion disk of superheated gas and dust. Matter in this disk moves at speeds approaching the speed of light, heating up to temperatures of millions of degrees. This process releases so much energy that it is emitted as powerful radiation, from radio waves to X-rays and gamma radiation. This radiation is capable of sterilizing any planet within a radius of thousands of light years, destroying atmospheres, breaking down organic molecules, and making life as we know it absolutely impossible. One of the brightest examples of such galaxies is the quasar, one of the most powerful and luminous objects in the universe. Quasars were first discovered in the 1960s and remained a mystery to astronomers for a long time. These objects looked like stars but emitted an incredible amount of energy, far more than any known star. Over time, scientists realized that quasars are not stars but the nuclei of distant galaxies, at whose centers lie supermassive black holes consuming matter at colossal rates. Some quasars are so bright that they can be seen from distances of billions of light years, even though they reside in galaxies that are themselves invisible due to the enormous distance. This means that the energy released by a quasar can exceed the luminosity of a trillion suns. To understand the scale of this phenomenon, imagine that all the energy that our Sun will produce over its entire 10 billion year lifetime is released by a quasar in just a few days. This is the level of power we are dealing with. The danger posed by quasars extends far beyond their incredible brightness. The radiation they emit is not just light, it is a deadly cocktail of high-energy particles and electromagnetic waves that can penetrate deep into space. If a planet were located even 1,000 light-years away from an active quasar, the radiation would be intense enough to strip away its atmosphere within a relatively short period on cosmic timescales. The ozone layer that protects Earth from harmful solar radiation would be obliterated instantly. The surface would be bombarded with X-rays and gamma rays, sterilizing any life forms and potentially rendering the planet uninhabitable for millions of years. Even if life somehow managed to survive deep underground or in ocean trenches, the entire ecosystem would collapse as the radiation destroyed the base of the food chain, photosynthetic organisms that depend on stable, moderate sunlight rather than the furious onslaught of a quasar's energy. But quasars are not the only manifestation of active galactic nuclei. There are also blazars, even more extreme versions of these cosmic monsters. A blazar is essentially a quasar whose jets of material ejected by the central black hole are pointed directly at Earth. These jets are streams of particles accelerated to nearly the speed of light, traveling along the magnetic field lines that thread through the accretion disk. When these jets are oriented toward us, we see their full fury, a beam of radiation so intense that it can outshine everything else in the galaxy. The term blazar comes from the combination of blaze and quasar, perfectly capturing the explosive nature of these objects. Observing a blazar is like looking down the barrel of a cosmic gun, with all its destructive power aimed directly at you. Fortunately for us, the nearest blazars are billions of light years away, so their radiation has weakened considerably by the time it reaches Earth. But for any civilization unfortunate enough to be located in the same galaxy as an active blazar, within a few thousand light years of it, the consequences would be catastrophic. The jets produced by blazars can extend for hundreds of thousands of light years, plowing through intergalactic space and creating enormous lobes of hot gas and magnetic fields. These jets are powered by the rotational energy of the black hole and the material falling into it, converted through complex electromagnetic processes into kinetic energy. The particles in these jets travel at such high speeds that they experience relativistic effects, time dilation, length contraction, and massive increases in energy. When these particles collide with the sparse gas that fills intergalactic space, they produce shockwaves and radiation that can be detected across vast cosmic distances. The power contained in a single jet from a blazar can exceed the total power output of thousands of galaxies like the Milky Way. This is destruction on a scale that defies human comprehension. Moving beyond active galactic nuclei, we encounter another category of dangerous galaxies: starburst galaxies. These are galaxies undergoing periods of extraordinarily rapid star formation, producing new stars at rates hundreds or even thousands of times higher than galaxies like our own Milky Way. While this might sound like a positive, creative process, and in many ways it is, starburst galaxies are also incredibly dangerous places. The rapid formation of massive stars leads to equally rapid stellar deaths, as these giant stars burn through their fuel in just a few million years before exploding as supernovae. A galaxy experiencing a starburst phase might see dozens or even hundreds of supernovae occurring every year, compared to the Milky Way's rate of roughly 1 or 2 per century. Each supernova is a cataclysmic event that releases as much energy in a few weeks as the Sun will produce in its entire lifetime. The explosion sends shockwaves rippling through the surrounding gas, compressing it and triggering the formation of new stars, which creates a feedback loop. But these supernovae also emit intense radiation and high-energy particles, cosmic rays, that flood the galaxy. For any planetary system caught in this stellar fireworks display, the consequences would be severe. The radiation from nearby supernovae could strip away planetary atmospheres, the shockwaves could disrupt the orbits of planets and comets, and the cosmic rays could bombard any surviving worlds for thousands of years. Complex life would struggle to evolve or persist in such an environment, as the constant barrage of radiation would cause devastating mutations and make the surface of planets extremely hostile. One spectacular example of a starburst galaxy is M82, also known as the Cigar Galaxy, located about 12 million light-years from Earth. M82 is undergoing a period of intense star formation triggered by a close encounter with its larger neighbor, the galaxy M81. The gravitational interaction between these two galaxies has compressed gas clouds in M82, igniting massive bursts of star formation. Observations of M82 reveal that it is producing stars at a rate about 10 times higher than the Milky Way, and the galaxy is being torn apart by the energy released from all these young, massive stars. Powerful winds of hot gas are streaming out from M82's center, driven by the combined force of stellar winds and supernova explosions. These galactic winds are so strong that they are blowing material completely out of the galaxy and into intergalactic space, a process that can strip a galaxy of the raw materials needed for future star formation. The violence occurring in M82 is visible even in optical light, where the galaxy appears surrounded by glowing filaments of gas stretched out like tendrils. In X-ray observations, the galaxy blazes even more intensely, revealing the superhot gas heated to millions of degrees by shock waves and stellar explosions. The center of M82 is so active that it has been described as a cosmic furnace, forging new stars and immediately destroying some of them in spectacular fashion. Any advanced civilization attempting to exist in such a galaxy would face extraordinary challenges. Constant radiation exposure, frequent supernova events nearby, and the general instability of the galactic environment would make long-term survival difficult at best. Starburst galaxies often result from galactic collisions or close encounters, and this brings us to another category of extremely dangerous cosmic environments: colliding and merging galaxies. When two galaxies come close enough for their gravitational fields to interact, the results can be spectacular and terrifying. Despite the enormous distances between individual stars within galaxies, which means that direct stellar collisions are rare, the gravitational forces involved in galactic interactions are immense and can completely reshape both galaxies over time. Gas clouds are compressed, triggering intense bursts of star formation. Stars are flung out of their original orbits, sometimes being ejected from the galaxies entirely. The supermassive black holes at the centers of the galaxies spiral toward each other, eventually merging in an event that releases gravitational waves powerful enough to ripple through the fabric of spacetime itself. The antennae galaxies, located about 70 million light-years away, provide a stunning example of galaxies in the midst of collision. These two spiral galaxies began their interaction a few 100 million years ago and are now locked in a gravitational embrace that will eventually result in their merger. The collision has triggered massive star formation in the regions where the galaxies overlap, creating brilliant clusters of young stars. Long tidal tails of stars, gas, and dust stretch out from the main bodies of the galaxies, resembling the antennae of an insect, hence the name. These tails are streams of material pulled out by gravitational forces, and they contain billions of stars that have been ripped from their original homes. Over the next few 100 million years, the two galaxies will continue to merge, their shapes becoming increasingly distorted until they finally settle into a single, larger elliptical galaxy. For any planetary systems caught in such a collision, the experience would be profoundly unsettling, though not immediately destructive. The individual stars are so far apart that actual collisions between stars are extremely unlikely. If two galaxies each containing 100 billion stars merge, perhaps only a handful of stellar collisions might occur. However, the gravitational disruption would be severe. Planetary systems could be torn apart as they pass close to other stars or dense regions of gas. Planets could be ejected from their solar systems, becoming rogue worlds drifting through interstellar space. The bursts of star formation triggered by the collision would flood the galaxies with radiation from young, hot stars and subsequent supernovae. The once stable galactic environment would become chaotic and unpredictable. Our own Milky Way galaxy is destined for such a collision. In approximately 4 billion years, we will collide with our nearest large neighbor, the Andromeda Galaxy. This event, while certain to occur, is not an immediate threat to humanity or Earth. By that time, our Sun will be approaching the end of its main sequence life and will be expanding into a red giant, making Earth uninhabitable regardless of the galactic collision. Nevertheless, the Milky Way Andromeda collision will be one of the most significant events in our local corner of the universe. Computer simulations of this future collision show that the two galaxies will pass through each other, with their shapes becoming severely distorted. They will then separate briefly before falling back together for another collision. This process will repeat several times over the course of about 2 billion years until the galaxies finally merge into a single massive elliptical galaxy that astronomers have whimsically nicknamed Milkomeda. During this merger process, the solar system, if it still exists in any recognizable form, has a small but non-zero chance of being ejected from the galaxy entirely. The gravitational interactions during the collision could alter the Sun's orbit around the galactic center, potentially flinging it into intergalactic space. While this might sound catastrophic, it would actually make little practical difference to any planets still orbiting the Sun. The Sun's gravitational hold on its planets is far stronger than the weak gravitational influence of the rest of the galaxy, so the solar system would remain intact even as it became an intergalactic wanderer. However, the night sky would change dramatically. Instead of seeing the Milky Way as a band of light across the sky, observers would see the entire merged galaxy as a spectacular elliptical structure, and the view would become increasingly distant over time as the solar system drifted further into the void between galaxies. Among the most enigmatic and potentially dangerous galaxies are those containing supermassive black holes that periodically devour entire stars in events known as tidal disruption events. These occur when a star wanders too close to a supermassive black hole and crosses the event horizon's tidal radius, the point at which the black hole's gravitational gradient becomes so steep that the tidal forces overcome the star's self-gravity. The star is literally stretched like taffy in a process called spaghettification, with the near side of the star being pulled much more strongly than the far side. The star is torn apart, with about half of its material falling into the black hole, while the other half is ejected at high velocities. As the captured material spirals into the black hole, it forms a temporary accretion disk that can shine with the brilliance of billions of suns for weeks or months before fading away. These tidal disruption events are relatively rare. In a typical galaxy, they might occur once every 10,000 to 100,000 years. But when they do happen, they are spectacular and deadly. The burst of radiation from the forming accretion disk can outshine the entire galaxy briefly, and it sends out powerful X-rays and ultraviolet radiation that would be lethal to any life forms in the vicinity. Telescopes have captured these events in distant galaxies, allowing astronomers to study the properties of otherwise dormant supermassive black holes. Each tidal disruption event provides a brief window into the feeding habits of these cosmic predators and reveals the extreme physics at play near the event horizon. The danger these events pose is not just theoretical. If our own galaxy's central black hole, Sagittarius A star, were to experience a tidal disruption event with a star that wandered too close, the entire galactic center would light up with radiation. Fortunately, we are located about 26,000 light-years from the galactic center, which provides considerable protection from such events. Nevertheless, the intense radiation would be detectable from Earth, and if we were significantly closer, say, a few thousand light-years, the effects could be much more concerning. The X-ray and gamma-ray flux could impact Earth's atmosphere, potentially causing ozone depletion and increasing surface radiation levels. Another class of extraordinarily dangerous galaxies includes those dominated by supermassive black hole binaries, pairs of supermassive black holes orbiting each other. These systems form when two galaxies merge and their central black holes eventually sink to the center of the newly formed galaxy through a process called dynamical friction. As the black holes orbit each other, they gradually spiral inward, their orbital period decreasing as they lose energy through gravitational radiation and interactions with nearby stars and gas. When they finally merge, the event releases an enormous burst of gravitational waves, ripples in spacetime that propagate outward at the speed of light. The merger of two supermassive black holes is one of the most energetic events in the universe, releasing more energy in gravitational waves in a fraction of a second than all the stars in the observable universe emit as light during that same time. The gravitational waves from such mergers can be detected by instruments like LIGO and Virgo when they involve smaller black holes, but supermassive black hole mergers produce waves at frequencies that require space-based detectors like the planned LISA mission to observe. The violence of these mergers is almost beyond comprehension. The space-time around the merging black holes is twisted and warped so severely that the normal rules of geometry break down. The newly formed, larger black hole can receive a kick from the asymmetric emission of gravitational waves, potentially causing it to recoil at speeds of thousands of kilometers per second. In extreme cases, this kick could be powerful enough to eject the merged black hole from its host galaxy entirely. For any civilization existing in a galaxy hosting a supermassive black hole binary, the final stages of the merger would be a time of considerable danger. The black holes would distort spacetime in their vicinity, potentially disrupting the orbits of nearby stars. Stars that pass too close to the binary might be ejected from the galaxy at high velocities in gravitational slingshot interactions. The region around the binary would become increasingly chaotic, with gas being heated and compressed, potentially triggering bursts of star formation or, conversely, being expelled from the galaxy. The gravitational waves themselves would pass harmlessly through most matter, but their passage would cause subtle oscillations in spacetime that could, in principle, be detected by sufficiently advanced instruments. We must also consider galaxies that harbor hypervelocity stars, stars that have been accelerated to speeds high enough to escape their galaxy's gravitational pull. These stars are typically produced by interactions with supermassive black holes or binary black hole systems. A binary star system that wanders too close to a supermassive black hole can be torn apart, with one star being captured by the black hole while the other is ejected at enormous velocity, sometimes exceeding 1,000 kilometers per second. These hypervelocity stars streak through the galaxy and can even escape into intergalactic space, becoming lonely wanderers in the cosmic void. The discovery of hypervelocity stars has opened new avenues for studying galactic dynamics and the properties of supermassive black holes. By tracing these stars' trajectories backward, astronomers can identify their points of origin and learn about the violent interactions that created them. For our purposes, these stars represent another way in which galaxies can be dangerous, not to themselves, but potentially to other systems. A hypervelocity star plowing through a region of space at such tremendous speeds could gravitationally disrupt any planetary systems it passes near. While the chances of a direct impact are vanishingly small due to the vast distances involved, the gravitational influence of a massive star moving at such high velocity could perturb the orbits of comets in distant Oort clouds, potentially sending showers of comets into intersolar systems on collision courses with planets. Let us turn our attention now to radio galaxies, another category of galactic danger. Radio galaxies are similar to quasars and blazars in that they are powered by supermassive black holes with active accretion disks, but they are typically observed in a different orientation. Instead of looking directly at the accretion disk or down the jet, we view radio galaxies from the side or at an angle, which allows us to see the enormous lobes of radio-emitting plasma that extend far beyond the visible galaxy. These lobes are created by the jets of particles ejected from the vicinity of the black hole, which plow into the intergalactic medium and create vast bubbles of energized gas. Some radio galaxies produce lobes that extend for millions of light years, far larger than the galaxies themselves. The energy contained in these lobes is staggering, and they can have significant effects on their surroundings. The hot gas in the lobes prevents cooling and the formation of new stars in the intergalactic medium, effectively creating enormous, dead zones, where new galaxies cannot form. The radio galaxies also produce powerful radiation across the electromagnetic spectrum, from long wavelength radio waves to X-rays. Any planetary system located within or near these radio lobes would be bathed in high-energy radiation, making the development of complex life extremely difficult. One of the most famous radio galaxies is Centaurus A, located about 13 million light-years from Earth. This galaxy is the result of a merger between a large elliptical galaxy and a smaller spiral galaxy, and the collision has triggered intense activity in the central black hole. Jets of material are being ejected perpendicular to the plane of the merged galaxy, creating enormous radio lobes that are visible in radio telescope images. In visible light, Centaurus A appears as a large elliptical galaxy with a dark dust lane across its center, the remnant of the spiral galaxy that was consumed. The violence of this system is impressive even at such great distances, and it serves as a reminder of the power contained within galactic nuclei. Another extreme category comprises gamma-ray burst host galaxies. Gamma-ray bursts, or GRBs, are the most energetic explosions known to occur in the universe, briefly outshining everything else in the sky in gamma rays. These events are thought to be produced by two primary mechanisms: the collapse of extremely massive stars in hypernovae explosions, or the merger of two compact objects such as neutron stars. The bursts themselves are beamed, concentrated into narrow jets of radiation, which means that the full energy of the event is directed along specific axes rather than being emitted in all directions. Despite this beaming, gamma-ray bursts are so energetic that they can be detected from billions of light-years away. If a gamma-ray burst were to occur in our galaxy, within a few thousand light-years of Earth, and with its beam directed toward us, the consequences would be catastrophic. The intense pulse of gamma rays would strike Earth's atmosphere, triggering chemical reactions that would destroy much of the ozone layer within seconds. The loss of the ozone layer would expose the surface to intense ultraviolet radiation from the sun, killing phytoplankton in the oceans and damaging terrestrial plants. The food chain would collapse, leading to mass extinction. Some scientists have proposed that gamma ray bursts might have been responsible for one or more of Earth's historical mass extinctions, though this hypothesis remains speculative and difficult to prove. The galaxies that host gamma ray bursts are typically those with active star formation, where massive stars are being born and dying in rapid succession. These are often irregular or spiral galaxies rich in gas and dust, the raw materials for star formation. The presence of even a few stars massive enough to produce gamma ray bursts makes such galaxies extremely hazardous places. The bursts themselves last anywhere from a few milliseconds to several minutes, followed by an afterglow that can persist for days or weeks as the jet of material interacts with the surrounding gas. During this time, the burst location shines across multiple wavelengths, from radio waves through visible light to X-rays and gamma rays. Research into gamma ray bursts has accelerated dramatically since the 1990s with the launch of dedicated satellites like the Compton Gamma Ray Observatory, SWIFT, and Fermi. These missions have detected thousands of gamma ray bursts, allowing astronomers to study their properties and understand their origins. The distribution of gamma ray bursts across the sky appears to be isotropic. They come from all directions equally, which suggests that they originate from distant galaxies spread throughout the universe rather than from sources within our own galaxy. This is fortunate for us, as it means that while gamma ray bursts are common on cosmic scales, they are sufficiently far away that we need not fear them as an immediate threat. We should also examine galaxies undergoing feedback processes that make them inhospitable to star formation and potentially to life. Feedback refers to processes by which energy from stars, supernovae, or active galactic nuclei heats or expels gas from a galaxy, preventing it from cooling and collapsing to form new stars. This might not sound particularly dangerous. After all, preventing star formation might seem like a peaceful process, but the mechanisms involved are violent and release enormous amounts of energy. Supernovae-driven winds can heat gas to millions of degrees and accelerate it to speeds of thousands of kilometers per second. Active galactic nucleus feedback can create even more powerful outflows, blowing gas completely out of the galaxy and into intergalactic space. Galaxies experiencing strong feedback are often red and dead. They have exhausted their star-forming gas and consist mainly of old, red stars. These elliptical galaxies are common in the universe, particularly in galaxy clusters, and they represent the endpoint of galactic evolution for many systems. The transition from an active, star-forming spiral galaxy to a quiescent elliptical galaxy is often triggered by a major merger with another galaxy, which funnels gas into the central black hole, triggering a period of intense active galactic nucleus activity. The black hole then essentially regulates its own feeding by expelling the surrounding gas, cutting off its food supply and simultaneously preventing new star formation throughout the galaxy. For any civilization existing in a galaxy undergoing this transition, the experience would be remarkable and potentially hazardous. The galaxy would be flooded with radiation from the active nucleus, intense winds would blow through the interstellar medium, and the rate of new star formation would plummet. Over millions of years, the galaxy would become increasingly sterile, with fewer young stars and less available gas for future generations of star formation. The night sky would gradually become dominated by old, red stars, and the vibrant spiral structure, if it existed, would be disrupted and eventually fade into a smooth elliptical distribution. Galaxy clusters themselves represent another dangerous environment. These are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies all held together by their mutual gravitational attraction. The space between galaxies in a cluster is filled with hot intracluster gas heated to temperatures of tens of millions of degrees, making it glow brightly in X-rays. This hot gas is so energetic that it can strip smaller galaxies of their own gas as they move through the cluster in a process called ram pressure stripping. The smaller galaxy plows through the intracluster medium like a ship through water, with the resistance stripping away its gas and leaving only its stars behind. The Coma cluster, located about 300 million light-years away, is one of the richest galaxy clusters known, containing thousands of galaxies. Observations of the Coma cluster reveal many examples of galaxies being stripped of their gas, their blue star-forming regions being torn away while their cores of older stars remain intact. These galaxies are being transformed by their environment, forced to stop forming stars by the hostile conditions in the cluster. Any civilization in one of these galaxies would witness their galaxy being slowly dismembered, its gas stripped away, its star formation ceasing, and its long-term future as a stellar nursery being terminated. The interactions between galaxies and clusters can also be violent. Galaxies don't orbit smoothly within clusters. They follow complex paths that occasionally bring them close to other galaxies, triggering interactions and sometimes mergers. The combined gravitational field of the entire cluster can also create tidal forces that distort galaxies, pulling them into elongated shapes or shredding smaller galaxies entirely. The dynamics of galaxy clusters are complex and chaotic, with galaxies moving at speeds of hundreds or thousands of kilometers per second relative to the cluster center. Let us consider another fascinating and dangerous type of galaxy, Seyfert galaxies. Named after Carl Seyfert, who first identified them in the 1940s, these galaxies are spiral galaxies with extremely bright nuclei that vary in brightness over time scales of months to years. Like quasars, Seyfert galaxies are powered by accretion onto supermassive black holes, but they are typically closer to us and less luminous than quasars. Seyfert galaxies come in two main types. Type 1 Seyferts show broad emission lines in their spectra, indicating we have a relatively clear view of the accretion disk, while Type 2 Seyferts show narrower emission lines, suggesting our view is partially obscured by dust and gas. The variability of Seyfert galaxy nuclei tells us that the source of their luminosity is compact. Changes in brightness propagate at the speed of light, so if a source becomes noticeably brighter or dimmer over a period of months, it must be small enough that light can cross it in that time. This constrains the size of the emitting region to be roughly light months across, remarkably small considering the enormous energies involved. The rapid variations also suggest that these galaxies can switch between active and quiescent states, potentially cycling through periods of intense radiation output and relative calm. For planets orbiting stars in Seyfert galaxies, particularly those located within a few thousand light-years of the nucleus, life would be hazardous and unpredictable. The radiation environment would fluctuate wildly as the central black hole goes through active and quiet phases. During active periods, the flux of X-rays and ultraviolet radiation could be intense enough to damage planetary atmospheres and irradiate surfaces. During quiet periods, conditions might be more benign, but the unpredictability would make the evolution of complex life challenging. Life thrives on stability, and the rapidly changing conditions in a Seyfert galaxy would provide anything but. We must also discuss the peculiar and dangerous class of galaxies known as low-ionization nuclear emission line regions, or liners. These galaxies have nuclei that emit spectral lines characteristic of low levels of ionization, suggesting different physical conditions than those found in Seyfert galaxies or quasars. The exact nature of the energy source in liners has been debated. Possibilities include low-level accretion onto supermassive black holes, shocks from galactic winds, or even star formation. Many nearby galaxies, including a substantial fraction of spiral and elliptical galaxies, show liner characteristics, suggesting that this might be a common phase in galactic evolution. If liners are powered by low-level black hole activity, they represent a less extreme but still potentially dangerous environment compared to Seyfert galaxies or quasars. The radiation output would be lower but still significant, and the presence of an active nucleus, even a mildly active one, would affect the surrounding galactic environment. Gas clouds near the nucleus would be heated and ionized, potentially disrupting star formation or triggering it through compression. The exact threat level posed by liner galaxies remains somewhat uncertain due to the ongoing debate about their energy sources, but they remind us that galactic nuclei can be active in many different ways, not all of which are immediately obvious or well understood. Another remarkable category of dangerous galaxies includes those with powerful stellar winds and outflows not necessarily associated with active galactic nuclei. In some galaxies, particularly those undergoing intense star formation, The combined stellar winds from massive young stars and subsequent supernova explosions can drive powerful galactic winds that expel material from the galaxy. These winds can reach speeds of thousands of kilometers per second and carry away not just gas but also dust and even some stars. The M82 galaxy mentioned earlier is an excellent example. Its starburst activity is driving a galactic wind that is actively reshaping the galaxy and stripping it of star-forming material. These galactic winds create extended regions of hot, shocked gas surrounding the galaxy. If another galaxy or a smaller dwarf galaxy were to encounter such a system, it might be stripped of its own gas by the powerful wind, much as galaxies and clusters are stripped by ram pressure. The winds also enrich the intergalactic medium with heavy elements, carbon, oxygen, iron, and others forged in stars, spreading these materials far beyond the galaxy's boundaries. This pollution of intergalactic space has important consequences for the chemical evolution of the universe and the formation of future generations of stars and planets. The phenomenon of tidal disruption extends beyond stars to entire galaxies. Dwarf galaxies that venture too close to larger galaxies can be torn apart by tidal forces, their stars stripped away and incorporated into the larger galaxy's halo. The Milky Way is currently in the process of consuming several dwarf galaxies, most notably the Sagittarius dwarf elliptical galaxy, which is being stretched into streams of stars that wrap around our galaxy. This process, called galactic cannibalism, is a normal part of the hierarchical growth of large galaxies. Over cosmic time, large galaxies like the Milky Way and Andromeda have grown by absorbing dozens or hundreds of smaller galaxies. For any planets or civilizations that might exist in these doomed dwarf galaxies, the tidal disruption would be a slow-motion catastrophe playing out over hundreds of millions of years. The gravitational influence of the larger galaxy would gradually perturb the orbits of stars in the dwarf galaxy, stretching it into elongated shapes. Some stars would be torn away and flung into the halo of the larger galaxy, while others might be pushed toward the dwarf galaxy's center. The overall structure of the dwarf galaxy would dissolve, its stars becoming part of the larger galaxy's stellar population. Individual planetary systems would likely survive this process intact. The distances between stars are so vast that direct encounters are rare, but the larger galactic environment would change dramatically. One of the most intriguing and potentially dangerous galactic phenomena involves magnetars, neutron stars with extraordinarily strong magnetic fields, billions of times more powerful than any magnetic field produced on Earth or around typical stars. While magnetars themselves are stellar remnants rather than galaxies, galaxies that contain multiple magnetars or that have high rates of core collapse supernovae capable of producing magnetars are particularly hazardous. Magnetars occasionally produce gigantic flares when their crusts crack due to magnetic stress, releasing enormous amounts of energy in gamma rays and X-rays. These magnetar flares can be detected from thousands of light-years away and would be lethal to life on planets in their vicinity. In December 2004, a magnetar flare from SGR 1806-20, located about 50,000 light-years from Earth on the other side of our galaxy, briefly disrupted Earth's ionosphere despite the enormous distance. If such a flare had occurred from a magnetar just a few hundred light-years away, the effects on Earth could have been severe. Galaxies with higher rates of core collapse supernovae, starburst galaxies, for example, would be expected to have more magnetars, making them particularly dangerous over long time scales. The probability of being affected by a magnetar flare in any given year is extremely low, but over millions or billions of years, the cumulative risk becomes significant. We should also consider galaxies with unusual morphologies that suggest violent histories. Peculiar galaxies, those that don't fit neatly into standard classification schemes, often show evidence of recent interactions or mergers. These might have disturbed structures, tidal tails, ring-shaped features, or multiple nuclei. Each of these features tells a story of gravitational chaos and violent encounters. The Cartwheel Galaxy, for example, located about 500 million light-years away, has a spectacular ring structure created when a smaller galaxy plunged through its center, triggering a wave of star formation that expanded outward like ripples on a pond. The collision compressed gas clouds, igniting a burst of star formation that has created a ring of brilliant blue stars and star clusters. Galaxies like the cartwheel remind us that galactic structures are not eternal and unchanging but rather dynamic systems that respond to gravitational perturbations. The ring structure in the cartwheel will eventually dissipate as the galaxy settles into a new equilibrium, but during the active phase, the regions of intense star formation would be flooded with radiation from massive young stars and would experience frequent supernova explosions. This would create a hazardous environment for any existing planetary systems, though it would also enrich the interstellar medium with heavy elements, potentially enabling the formation of rocky planets and, eventually, conditions suitable for life once the intense activity subsided. Another class of dangerous galaxies includes those in the process of being tidally stripped by their neighbors or by the gravitational field of a galaxy cluster. The process of tidal stripping creates spectacular visual features, streams and tails of stars stretching across space, but it also represents a galaxy being pulled apart by forces beyond its control. The stars in these tidal streams are being removed from their original galactic homes and scattered into intergalactic space. Over time, some will fall into the larger galaxy doing the stripping, while others might remain in the streams for billions of years, gradually dispersing as they orbit in the gravitational potential of the cluster or galaxy group. The NGC 4676 system, known as the mice galaxies due to their long tidal tails resembling mouse tails, provides a beautiful example of this process. These two spiral galaxies are in the midst of a collision that has drawn out long streams of stars and gas. The tails extend for hundreds of thousands of light years and contain billions of stars that have been pulled from the main bodies of the galaxies. Eventually, the two galaxies will merge, and the tidal tails will likely fall back into the merged system or disperse into intergalactic space. For stars in these tails, their galactic environment has been fundamentally altered. They now exist in a diffuse, low-density environment far from the main concentration of their galaxy's mass. Turning to the realm of dark matter, we should consider that while dark matter doesn't emit light or interact electromagnetically, it does interact gravitationally and comprises about 85% of all matter in the universe. Galaxies are embedded in massive halos of dark matter that extend far beyond their visible boundaries. While dark matter itself isn't dangerous in any direct sense, it passes through normal matter with virtually no interaction. The gravitational effects of dark matter halos play crucial roles in galactic dynamics and interactions. The dark matter halos of colliding galaxies interact first, long before the visible components begin to merge, and these interactions help shape the outcome of galactic mergers. Some theories propose that dark matter might not be completely collisionless but might interact weakly through forces other than gravity. If this self-interacting dark matter exists, it could lead to interesting phenomena such as cores and dark matter halos or even the separation of dark matter from visible matter during galactic collisions. The Bullet Cluster, a system of two colliding galaxy clusters, provides evidence for dark matter's existence by showing that the mass distribution inferred from gravitational lensing is separated from the hot gas visible in X-rays. This separation occurred because the dark matter is collisionless and passed through the collision unimpeded, while the gas interacted and was slowed down by electromagnetic forces. While we're discussing exotic physics, we should mention that some galaxies might harbor primordial black holes, hypothetical black holes that formed in the early universe from density fluctuations rather than from stellar collapse. These black holes, if they exist, could range in mass from tiny fractions of a gram to thousands of solar masses. A galaxy containing a significant population of primordial black holes might be a hazardous place due to the increased probability of close encounters between planetary systems and these invisible gravitational traps. A primordial black hole passing through a solar system could gravitationally perturb planets, potentially ejecting them from the system or sending comets from the outer system into the inner system. The search for primordial black holes continues, with astronomers using gravitational lensing and other techniques to constrain their abundance. If they make up a significant fraction of dark matter, they would have important implications for galactic dynamics and cosmic structure formation. However, current observations suggest that primordial black holes, if they exist, cannot make up all of the dark matter. Their gravitational effects would have been detected in various observations if they were that abundant. Nevertheless, they remain an intriguing possibility and a reminder that the universe might contain surprises we haven't yet discovered. Let us also examine galaxies at the edge of the observable universe, those we see as they were in the early universe shortly after the Big Bang. These ancient galaxies formed when the universe was less than 1 billion years old, and they provide windows into cosmic history. Many of these early galaxies are small, irregular systems undergoing intense star formation. They are the building blocks that would later merge to form the large galaxies we see in the modern universe. The environment in these early galaxies would have been extraordinarily harsh, high rates of star formation leading to frequent supernovae, intense radiation fields, and turbulent gas dynamics. The metallicity, the abundance of elements heavier than hydrogen and helium, would have been lower than in modern galaxies, meaning that planets forming in these systems would have been composed primarily of lighter elements. The James Webb Space Telescope has recently begun to reveal these distant galaxies in unprecedented detail, showing that some were larger and more structured than previous models predicted. These observations are forcing astronomers to rethink theories of galaxy formation and evolution. Some early galaxies appear to contain supermassive black holes that are larger than expected for their age, raising questions about how black holes grew so rapidly in the early universe. If these observations are confirmed, they might indicate that supermassive black holes formed through different mechanisms than previously thought, perhaps from the direct collapse of gas clouds rather than through the gradual growth of smaller black holes. For completeness, we should discuss galaxies at the opposite end of the spectrum, those that are dying or dead. Red and dead elliptical galaxies, as mentioned earlier, have exhausted their gas supplies and are no longer forming stars. Their stellar populations are aging, and without new star formation, these galaxies will gradually fade over trillions of years as their stars burn out. While this might seem peaceful, the death of a galaxy is a form of cosmic tragedy. A system that once bustled with stellar birth and evolution has fallen silent, its creative era ended. Any civilizations that might have arisen in such galaxies would find themselves in an aging environment, with fewer resources and a dimming future as the stars they depend on grow old and die. The ultimate fate of all galaxies in our local group, assuming the accelerating expansion of the universe continues, is isolation. As dark energy drives the expansion of space, galaxies outside our local group will recede from us ever faster, eventually crossing the cosmic horizon beyond which light can no longer reach us. In the far future, trillions of years hence, observers in the merged Milkomeda galaxy will look out and see an empty universe, with only the stars of their own galaxy visible. All evidence of the broader cosmos, other galaxy clusters, the cosmic microwave background, the large-scale structure of the universe, will have receded beyond detection. Future civilizations might have no way of knowing that the universe is larger than their single galaxy, and the grand cosmic story we can see today will be hidden from them forever. This brings us to a philosophical consideration: the danger posed by ignorance of cosmic threats. Advanced civilizations must be aware of the hazards posed by their galactic environment to survive long-term. A civilization in a galaxy with an active nucleus must understand the radiation environment and potentially take measures to protect themselves or their home world. A civilization in a galaxy destined to merge with another must plan for the changes that will occur. Ignorance of cosmic threats doesn't make them less dangerous. It simply makes them more likely to catch civilizations unprepared. Throughout this exploration, we've examined active galactic nuclei that flood space with deadly radiation, starburst galaxies torn apart by their own stellar fecundity, colliding galaxies that reshape their structures through gravitational violence, and numerous other hazardous galactic environments. Each of these represents a different way in which the universe can be hostile to life. Yet life, as we know from Earth's history, is remarkably resilient and adaptable. Organisms have survived mass extinctions, dramatic climate changes, and bombardment by cosmic rays and solar flares. It's not inconceivable that life, perhaps even intelligent life, could emerge and persist even in some of the dangerous galactic environments we've discussed, though such life might need to be very different from life on Earth, perhaps living deep underground or in heavily shielded environments. The study of dangerous galaxies also provides insights into the conditions necessary for life. By understanding what makes certain galaxies hazardous, we can better identify which galaxies and which regions within galaxies might be most suitable for life. The concept of a galactic habitable zone has been proposed. Regions within galaxies where conditions are either too violent for stable planetary systems to exist nor too devoid of heavy elements for rocky planets and complex chemistry to develop. In the Milky Way, this habitable zone is thought to be an annulus, a ring-shaped region, located at intermediate distances from the galactic center, far enough to avoid the intense radiation and frequent supernovae near the center, but close enough to have sufficient metallicity for Earth-like planets to form. Our solar system resides comfortably within this galactic habitable zone, about halfway out from the galactic center. This location provides us with relative stability. We're in a region of the galaxy where supernovae are rare but not unknown, where the metallicity is sufficient for rocky planet formation, and where we're protected from the intense radiation of the galactic nucleus. We're also located between the spiral arms of the galaxy, which means we don't frequently encounter the giant molecular clouds and active star formation regions that populate the spiral arms. This inter-arm location provides additional stability, reducing our exposure to nearby supernovae and intense stellar radiation. The concept of cosmic habitability extends beyond individual galaxies to galaxy clusters and superclusters. Dense galaxy clusters might be less suitable for life due to the high temperatures of the intracluster medium, the frequent interactions between galaxies, and the stripping of gas from galaxies. In contrast, galaxies in lower density environments, like those in galaxy groups or in the field, might offer more stable conditions over long time scales. The Milky Way belongs to the local group, a relatively small collection of galaxies dominated by the Milky Way and Andromeda, with numerous smaller dwarf galaxies. This is a relatively benign environment compared to the violent galaxy clusters we've discussed. As we contemplate the dangers posed by various types of galaxies, we must also acknowledge that danger is relative and depends on the time scales considered. On human time scales, even the most dangerous galaxies pose no immediate threat to Earth. We are protected by the vast distances of space, which shield us from all but the most extreme cosmic events. On time scales of millions or billions of years, however, the galactic environment becomes increasingly important. The future collision with Andromeda will reshape the Milky Way. The evolution of the Sun will eventually make Earth uninhabitable. Nearby supernovae or gamma ray bursts could potentially impact Earth's biosphere. Understanding these long-term threats is essential for any species with aspirations of surviving for geological or cosmic time scales. The search for extraterrestrial intelligence takes on new dimensions when we consider the dangers posed by various galactic environments. The Drake equation, which attempts to estimate the number of communicating civilizations in the galaxy, includes terms for the rate of star formation, the fraction of stars with planets, and the fraction of planets where life arises. But perhaps it should also include a term for the galactic habitability, the fraction of the galaxy where conditions are suitable for life to arise and persist long enough to develop intelligence and technology. In galaxies with active nuclei, intense starburst activity, or frequent mergers, this fraction might be very small. In quiescent spiral galaxies like the Milky Way, it might be much larger. This leads to the question of whether some types of galaxies are more likely than others to host intelligent life. Elliptical galaxies, despite being common, might be poor hosts for advanced civilizations because they lack ongoing star formation and have old stellar populations. Planets in elliptical galaxies would have formed long ago, and any civilizations that arose would be ancient if they still exist. Spiral galaxies with ongoing but moderate star formation might be ideal. They continuously produce new generations of stars and planets, have substantial regions of relative stability, and possess sufficient metallicity for complex chemistry. Irregular galaxies might be too chaotic, with unpredictable star formation and potentially higher rates of supernova events. The implications for SETI, the search for extraterrestrial intelligence, are significant. Perhaps our search should focus on galaxies and regions within galaxies that are most likely to be habitable. Within our own galaxy, We might prioritize stars in the galactic habitable zone, avoiding regions too close to the center or too far out on the fringes. When searching for technosignatures or biosignatures in other galaxies, we might focus on spiral galaxies rather than ellipticals, and avoid galaxies with active nuclei or ongoing mergers. Of course, this assumes that extraterrestrial life has similar requirements to life on Earth, which may not be true, but it's a reasonable starting point given that Earth is our only example of a planet that definitively hosts life. The study of dangerous galaxies also informs our understanding of cosmic evolution and the life cycle of galaxies. Galaxies are not static objects but dynamic systems that evolve over cosmic time. They grow through mergers and accretion of gas, they undergo periods of intense star formation and quiescence, their central black holes alternate between active and dormant states, and they interact with their environments in complex ways. The dangerous phenomena we've discussed, active nuclei, starbursts, collisions, are all part of this evolution. They represent different phases or different outcomes of galactic development, each teaching us something about the physical processes that govern these immense systems. Looking toward the future of astronomy, upcoming telescopes and instruments will provide even more detailed views of dangerous galaxies. The James Webb Space Telescope is already revealing early galaxies in unprecedented detail. The next generation of ground-based extremely large telescopes, such as the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope, will provide even higher resolution observations of nearby galaxies and their nuclei. Gravitational wave detectors like LISA will allow us to detect supermassive black hole mergers throughout the universe. These new capabilities will undoubtedly reveal more about the violent processes occurring in galaxies and will likely surprise us with phenomena we haven't yet imagined. In considering the most dangerous galaxies, we must also reflect on what makes them fascinating. These objects represent nature operating at its most extreme, pushing the boundaries of physical processes and creating conditions unlike anything we experience in our everyday lives or even in most of the universe. They are natural laboratories where we can study physics under extreme conditions, intense gravity near black holes, matter moving at relativistic speeds in jets, nuclear reactions in starburst regions, and gravitational interactions during mergers. Each dangerous galaxy teaches us something new about the laws of nature and the behavior of matter and energy under extraordinary circumstances. The dangers posed by these galaxies are also reminders of our cosmic vulnerability. Earth and humanity exist in a relatively safe corner of a relatively benign galaxy, but we are not immune to cosmic threats. Throughout Earth's history, mass extinctions have been triggered or exacerbated by extraterrestrial events, asteroid impacts most famously, but potentially also nearby supernovae, solar storms, or other phenomena. Understanding the range of cosmic hazards helps us appreciate our good fortune in existing when and where we do, and it motivates efforts to ensure humanity's long-term survival, whether through protecting Earth or eventually expanding beyond it. As we conclude this exploration of the most dangerous galaxies, it's worth emphasizing that dangerous is a label we apply from a human perspective. The universe itself is neither dangerous nor safe, it simply is. The processes we've discussed, from active galactic nuclei to colliding galaxies, are natural consequences of the laws of physics operating on cosmic scales. They are part of the grand tapestry of cosmic evolution that has unfolded over the 13.8 billion years since the Big Bang. These processes have created the elements necessary for life, sculpted the large-scale structure of the universe, and produced the rich diversity of galaxies we observe. In the grand scheme, even the most violent galactic phenomena are creative as well as destructive. Supernovae that sterilize nearby space also forge heavy elements and disperse them into the interstellar medium, enriching future generations of stars and planets. Colliding galaxies trigger intense star formation, creating new stellar populations and potentially new planetary systems. Active galactic nuclei might clear out gas and halt star formation in one region while compressing gas and triggering it elsewhere. The universe's violence and creativity are two sides of the same coin, both stemming from the fundamental forces and particles that comprise physical reality. The story of dangerous galaxies is ultimately a story about the universe's capacity for transformation. Nothing in the cosmos is permanent. Not galaxies, not stars, not even the fabric of space-time itself according to some theories. Everything evolves, changes, interacts, and eventually transforms into something new. The dangerous galaxies we've examined are simply galaxies undergoing particularly dramatic transformations, caught in moments of intense change that will eventually give way to new equilibria. In this sense, they are no different from quieter galaxies except in the pace and intensity of their evolution. For humanity, understanding dangerous galaxies serves multiple purposes. Scientifically, it advances our knowledge of astrophysics, cosmology, and the behavior of matter under extreme conditions. Philosophically, it provides perspective on our place in the universe and the contingencies that have allowed us to exist. Practically, it informs our assessment of cosmic risks and our strategies for long-term survival as a species. And aesthetically, it reveals the universe's capacity for spectacular beauty even in its most violent moments. The intricate structures of colliding galaxies, the brilliant light of quasars, the ghostly streams of tidal tails stretching across space. As we look up at the night sky, we see light that has traveled for years, centuries, millennia, or even billions of years to reach us. Some of that light comes from galaxies that are currently undergoing the violent processes we've discussed. We see them not as they are now but as they were in the past. The more distant the galaxy, the further back in time we observe. This means that our view of the universe is necessarily historical, a cosmic museum displaying the evolution of galaxies across time. The dangerous galaxies we observe in the distant universe might have settled into quiescence by now. Their violent phases ended billions of years ago. Conversely, some of the peaceful-looking nearby galaxies might be destined for dramatic futures we cannot yet see. This temporal aspect of astronomical observation adds another layer to our understanding of dangerous galaxies. We are not just mapping which galaxies are dangerous in space, but also when they are dangerous in time. Different types of dangerous phenomena dominate at different cosmic epochs. Quasars were more common in the early universe when galaxies were actively growing and merging, while the current universe has fewer quasars but more red and dead elliptical galaxies. Understanding this evolution helps us piece together the history of the universe and predict its future. In the end, the most dangerous galaxies ever discovered serve as monuments to the universe's power and complexity. They challenge our understanding, push the limits of our instruments, and inspire awe with their sheer scale and energy. They remind us that while Earth might seem like the center of our existence, it is actually a tiny oasis in a vast cosmos filled with wonders and terrors beyond imagination. The study of these galaxies is not just an academic exercise but a journey into the heart of cosmic reality, revealing the mechanisms that have shaped the universe and continue to drive its evolution. As astronomical technology advances and our understanding deepens, we will undoubtedly discover even more extreme galaxies and phenomena. The universe has consistently proven more strange, more violent, and more magnificent than our theories predicted. Each new discovery opens new questions and reveals new mysteries to solve. The dangerous galaxies we know today may seem tame compared to what we might discover tomorrow. This is the excitement of astronomy. The frontier is limitless, and the universe's capacity to surprise us appears boundless. To anyone looking up at the stars, remember that behind those peaceful points of light lie entire galaxies, some of them cosmic cauldrons of violence and energy. The universe is not a quiet place, and danger lurks in scales beyond human comprehension. But it is also beautiful, awe-inspiring, and endlessly fascinating. The most dangerous galaxies remind us of our place in the cosmos, small and vulnerable, yes, but also possessed of the intelligence and curiosity to understand the forces that govern the universe. That understanding is itself a kind of power, the ability to comprehend the incomprehensible and to find meaning in the cosmic chaos. In studying the universe's most dangerous places, we honor our capacity for reason and our drive to explore, even when exploration reveals how vast and indifferent the cosmos truly is. The universe contains mysteries within mysteries, and among the most perplexing are ultra-diffuse galaxies, strange objects that challenge our understanding of what a galaxy can be. These ghostly structures are as large as the Milky Way but contain only a tiny fraction of its stars, making them so dim and spread out that they are incredibly difficult to detect. Their stars are scattered so thinly through space that the galaxies appear almost transparent, like cosmic phantoms drifting through the void. What makes these galaxies potentially dangerous is not their current state, but what they might become, and what they might hide. Some ultra-diffuse galaxies appear to contain surprisingly little dark matter, which contradicts our understanding of galaxy formation. Galaxies should not be able to form or maintain their structure without substantial dark matter halos to provide gravitational scaffolding. Yet these anomalous objects exist, suggesting either that our theories are incomplete, or that these galaxies have undergone catastrophic events that stripped away their dark matter. If the latter is true, then ultra-diffuse galaxies might be the remnants of normal galaxies that suffered extreme tidal stripping or high-speed collisions that tore them apart. There would be cosmic crime scenes, evidence of violence so severe it fundamentally altered the galaxy's nature. The existence of such stripped galaxies implies regions of space where gravitational interactions are intense enough to dismember even massive structures. Galaxy clusters containing multiple ultra-diffuse galaxies would be zones of exceptional gravitational chaos, where the normal rules of galactic dynamics break down. Any star system unfortunate enough to be caught in the crossfire of these interactions would experience gravitational perturbations capable of destabilizing planetary orbits, or even ejecting planets entirely from their solar systems. The night sky from such a world would be a strange sight indeed. Instead of a clear galactic disk or spiral structure, observers would see scattered clumps of stars distributed across vast regions of near emptiness. Moving to a different extreme, we encounter compact elliptical galaxies, tiny but incredibly dense stellar systems that pack millions or billions of stars into regions just a few thousand light-years across. These objects are thought to be the stripped cores of much larger galaxies, the survivors of close encounters or collisions that tore away their outer layers and left only their dense central regions. The stellar density in these compact ellipticals is extraordinary, far higher than in normal galaxies. Stars are packed so closely together that gravitational interactions between them become common, leading to frequent close encounters and occasional collisions. In such an environment, planetary systems would face constant threats. A star passing within a light-year or two of a solar system could gravitationally perturb the outer planets and send comets from the Oort cloud plummeting toward the inner system. Closer encounters could be even more disruptive, potentially ejecting planets from their orbits or transferring them between stars. The high stellar density would also mean that supernova explosions occur relatively nearby on a regular basis, bathing the entire compact galaxy in elevated levels of cosmic rays and high-energy radiation. Life attempting to evolve in such a galaxy would face a gauntlet of challenges unlike anything experienced in more typical galactic environments. The phenomenon of galactic harassment deserves attention as another mechanism by which galaxies can become dangerous to their inhabitants. This process occurs when a small galaxy repeatedly passes through or near a larger galaxy or galaxy cluster, experiencing tidal forces and ram pressure stripping with each passage. Unlike a single dramatic collision, harassment involves multiple encounters over hundreds of millions or billions of years, gradually transforming the victim galaxy. With each passage, more gas is stripped away, more stars are pulled out into tidal streams, and the galaxy's structure becomes increasingly disturbed. For civilizations in a galaxy undergoing harassment, the experience would be one of slow decline rather than sudden catastrophe. Each passage through the cluster or past the larger galaxy would bring new waves of disruption. Tidal forces would heat the stellar disk, triggering instabilities and potentially driving stars out of their stable orbits. Gas would be stripped away, reducing the material available for future star formation. Over millions of years, the galaxy would transform from a vibrant spiral into a gas-poor irregular galaxy or eventually into a dwarf elliptical. The inhabitants would witness their galaxy dying by degrees, each encounter bringing new devastation until finally nothing remained but a stellar remnant. Let us examine the curious case of ring galaxies in more detail. These structures form when a smaller galaxy makes a nearly head-on collision with a larger disk galaxy, passing through its center. The collision sends a density wave rippling outward through the disk, compressing gas and triggering star formation in an expanding ring. The Higgs object is perhaps the most famous example, A nearly perfect ring of bright blue stars surrounds a yellow core, with a gap between them so large and empty that background galaxies can be seen through it. The symmetry is striking and somewhat unsettling, as if the galaxy were an enormous cosmic eye staring back at us. The formation of such rings involves tremendous violence despite their beautiful appearance. The intruding galaxy punches through the disk, its gravitational field creating shockwaves that compress gas clouds and ignite massive star formation. The ring expands outward at speeds of hundreds of kilometers per second, sweeping up gas and triggering successive waves of stellar birth. Behind the ring, the disk is left depleted and disrupted. Any planets in the path of the expanding ring would find themselves in a suddenly active region of space, surrounded by newly forming massive stars that would flood the area with intense radiation and eventually explode as supernovae. The timescale for the ring's expansion means that a given region might experience just a few million years of intense star formation before the ring passes and conditions return to relative calm. But those few million years would be extraordinarily hazardous. Polar ring galaxies present another peculiar structure with implications for galactic habitability. These objects consist of a central galaxy, typically an elliptical or lenticular, surrounded by a ring of stars, gas, and dust that orbits in a plane nearly perpendicular to the main body of the galaxy. The formation mechanism likely involves the accretion of material from a smaller galaxy that approached on a particular trajectory, with its material settling into a polar orbit due to angular momentum conservation. The result is a galaxy with two distinct components rotating at nearly right angles to each other. The dynamical complexity of polar ring galaxies creates an environment rife with orbital instabilities. The gravitational fields of the two components interact in complex ways, creating regions where orbits are chaotic rather than stable. Stars and gas clouds can be transferred between the components, and the tidal forces at the interface between them can be substantial. For planets orbiting stars near this interface, the gravitational environment would be highly variable, with the combined pull of both galactic components creating time-varying forces. Over geological timescales, these forces could drive planets into eccentric orbits, or even eject them from their systems entirely. Shell galaxies represent yet another class of peculiar structures that reveal violent histories. These elliptical galaxies are surrounded by faint shells or ripples of stars that form concentric patterns around the galaxy's center. These shells are thought to be the remnants of smaller galaxies that were cannibalized by the elliptical, their stars stripped away and spread into these distinctive patterns. The shells form through a process called phase wrapping. As the smaller galaxy is torn apart, its stars continue to orbit the larger galaxy but gradually spread out along their orbital paths. Stars that started together gradually separate based on their slightly different orbital velocities, creating the observed shell patterns. The presence of shells indicates that the galaxy has recently consumed one or more smaller galaxies, and this process would have been traumatic for any planetary systems involved. The tidal forces during the merger would have been severe, particularly for stars that passed close to the larger galaxy's core. Some stars would have been accelerated to high velocities and ejected, while others would have had their orbits drastically altered. The shells we see are the survivors, stars that remained gravitationally bound but were scattered into their current unusual orbits. Any planets around these stars would have experienced dramatic changes in their galactic environment, potentially being subjected to close encounters with other stars during the chaotic merger process. Luminous infrared galaxies, or LIRGs, deserve careful examination as another category of extreme galactic environments. These galaxies emit most of their energy in the infrared portion of the spectrum, often outshining normal galaxies by factors of 10 or more in total luminosity. The infrared emission comes from dust that has been heated by intense star formation or active galactic nucleus activity. Many LIRGs are galaxies in the midst of mergers, where the collision has funneled enormous amounts of gas into the central regions, triggering starbursts, and sometimes activating the central black hole. The most extreme examples are ultraluminous infrared galaxies, or ULIRGs, which emit more than 1 trillion times the Sun's luminosity primarily in the infrared. These objects are cosmic furnaces, with star formation rates that can exceed 1,000 solar masses per year, compared to the Milky Way's leisurely pace of just a few solar masses per year. The centers of Ullrgs are often so obscured by dust that they are completely invisible in optical light, appearing only as bright infrared sources. The dust temperatures can reach hundreds of degrees, and the radiation field is intense enough to dissociate molecules and ionize atoms throughout large volumes of the galaxy. For life to exist in such galaxies would require extreme adaptations. The dust that makes these galaxies so luminous in the infrared would also block visible light, creating a dim, reddish environment even during the day on any planets. The intense radiation field would require any life forms to have robust DNA repair mechanisms or equivalent systems to cope with constant radiation damage. The high rate of star formation would mean frequent supernovae, and the density of stars in the starburst regions would be high enough that close stellar encounters would be more common than in normal galaxies. It's difficult to imagine complex life evolving in such conditions, though perhaps simple, radiation-resistant organisms could persist in sheltered locations. Green P galaxies add another dimension to our catalog of unusual and potentially dangerous galactic environments. These small, compact galaxies are so named because they appear as small green dots in astronomical survey images, the green color resulting from intense emission from ionized oxygen. Green Ps are undergoing intense star formation for their size, with rates that would exhaust their gas reservoirs in just tens of millions of years if sustained. They are thought to be nearby analogues of the types of galaxies that were common in the early universe, providing windows into cosmic history. The intense star formation in green Ps creates conditions reminiscent of the early universe when star formation rates were generally much higher than today. The galaxies are flooded with ultraviolet radiation from massive young stars, which ionizes the surrounding gas and creates enormous regions of ionized hydrogen and oxygen. This radiation is so intense that it can escape from the galaxies entirely, leaking out into intergalactic space. In the early universe, radiation from countless galaxies like these is thought to have reionized the universe, transforming it from a neutral state back to an ionized state a few hundred million years after the Big Bang. Any planets within green P galaxies would experience extreme ultraviolet exposure, far beyond what Earth receives from the Sun. Atmospheric ozone would be destroyed, and the surfaces would be bathed in radiation capable of breaking down organic molecules. Water would be photodissociated into hydrogen and oxygen, with the light hydrogen potentially escaping to space. Maintaining liquid water on a planet's surface would be challenging at best, and the development of complex life would require either deep ocean habitats or subsurface refuges where organisms could hide from the relentless radiation. Dwarf starburst galaxies, though small, can be remarkably violent. These tiny galaxies, some containing only a few million stars compared to the Milky Way's hundreds of billions, occasionally undergo intense bursts of star formation that, relative to their size, rival or exceed the activity in much larger starburst galaxies. The trigger is often an influx of gas, perhaps from a small companion galaxy being absorbed or from gas accretion from the intergalactic medium. The resulting starburst can be brief but spectacular, with the entire galaxy lighting up as massive stars form and quickly begin to die. The blue compact dwarf galaxy NGC 1705 exemplifies this phenomenon. Despite its small size, it is experiencing vigorous star formation that has created clusters of massive stars in its center. Supernova explosions from these stars are driving powerful winds that are beginning to blow gas out of the galaxy entirely. For a galaxy this small, losing gas to stellar winds can be catastrophic. Unlike large galaxies that have deep gravitational wells capable of retaining heated gas, dwarf galaxies can lose their gas reservoirs permanently. This means that a starburst in a dwarf galaxy might be a one-time event, after which the galaxy has no material left to form new stars and gradually fades as its stellar population ages. Tidal dwarf galaxies represent a fascinating and transient category of galactic objects. These are not galaxies that formed independently in the early universe but rather structures that condense from tidal tails during galactic collisions. When two large galaxies collide, their gravitational interaction pulls out long streams of gas and stars called tidal tails. If sufficient material accumulates in a particular region of a tidal tail, it can gravitationally collapse to form a self-bound structure that resembles a dwarf galaxy. These tidal dwarfs are ephemeral. Most will eventually fall back into one of the parent galaxies. but during their brief existence, they can form stars and develop their own internal structure. What makes tidal dwarf galaxies particularly interesting from a habitability perspective is that they are thought to contain little or no dark matter. Dark matter doesn't get pulled out into tidal tails as readily as normal matter because it has a more extended distribution and doesn't experience the same tidal forces. This means that tidal dwarfs are composed almost entirely of normal matter, stars, gas, and dust, with their self-gravity being provided by this visible matter alone. Without dark matter to stabilize them, tidal dwarfs may be more susceptible to disruption from passing galaxies or internal instabilities. Stars forming in tidal dwarfs would inhabit a galactic environment fundamentally different from those in normal galaxies, with potentially important implications for long-term orbital stability. The centers of galaxies harbor their own unique dangers beyond the supermassive black holes we've already discussed. The nuclear star cluster, the dense concentration of stars surrounding the black hole, is a region of extraordinary stellar density. In the Milky Way's nuclear star cluster, stars are packed thousands of times more densely than in the Sun's neighborhood. Collisions between stars, while still rare on human timescales, occur frequently enough that the cluster likely contains many collision products, unusual stars formed by the merger of two normal stars. The environment near the galactic center is harsh in other ways too. The supermassive black hole's tidal forces create a region called the tidal disruption radius where stars can be torn apart if they approach too closely. Beyond this radius, but still relatively close to the black hole, stellar orbits become highly eccentric and subject to relativistic effects. Some stars near the center of the Milky Way have been observed with orbital velocities exceeding a few % of the speed of light as they whip around the black hole on extremely elongated orbits. Any planets around such stars would experience wild variations in their galactic environment as they swung from distant aphelion to close periastron passages near the black hole. The concept of hypercompact stellar systems deserves attention as perhaps the most extreme environments where stars can exist. These are ultra-dense clusters that may form in the centers of galaxies or as the remnant cores of tidally stripped dwarf galaxies. In hypercompact stellar systems, stars can be separated by average distances of just a few light days, incredibly close on astronomical scales. At such densities, gravitational interactions dominate the dynamics, with stars frequently exchanging partners in binary systems, colliding, or being ejected from the cluster entirely. The astrophysics of hypercompact stellar systems is exotic and not yet fully understood. At such high densities, relativistic effects become important even for stars orbiting at subrelativistic velocities, because the concentrated mass creates significant spacetime curvature. The system can emit gravitational waves at detectable levels, and the frequent stellar interactions create a population of unusual objects, blue stragglers formed by stellar mergers, exotic binary systems, and possibly intermediate mass black holes formed by runaway collisions. For any hypothetical planets in such systems, survival would be unlikely. The gravitational chaos would quickly strip planets from their host stars or destabilize their orbits beyond habitability. Galactic fountains and chimneys represent another mechanism by which galaxies can become dangerous to specific regions within them. When multiple supernovae occur in a concentrated area over a short time period, their combined energy can blow a hole through the galactic disk, creating a chimney through which hot gas fountains out into the galactic halo. This gas, enriched with heavy elements from the supernovae, rises thousands of light years above the disk before cooling and falling back down, often in a different location. The cycle can repeat, with the fallen gas forming new stars that eventually explode and drive new fountains. These galactic fountains create vertical structures in the disk, channels through which hot, ionized gas flows at high velocities. Any star system passing through or near one of these fountains would be exposed to intense heat and radiation. The fountaining gas can reach temperatures of millions of degrees, and while the density is low, the sheer volume and velocity of the material creates a hostile environment. The fountains also redistribute heavy elements within the galaxy, potentially enriching some regions while depleting others, which would affect the metallicity available for forming new planetary systems. The Fermi bubbles discovered in our own Milky Way provide evidence that even relatively quiescent galaxies can experience episodes of violence. These enormous structures extend roughly 25,000 light-years above and below the galactic center, forming a shape reminiscent of an hourglass. They emit gamma rays and were likely created by a burst of activity from the central black hole or by an intense period of star formation in the nuclear regions several million years ago. The bubbles represent a huge reservoir of energy, roughly equivalent to 100,000 supernovae, that was injected into the galactic halo in a geologically brief period. The creation of the Fermi bubbles would have been a significant event for the Milky Way. If they were created by an active galactic nucleus outburst, the black hole would have briefly fed at a much higher rate than its current dormant state, emitting powerful jets that carved out the bubbles in the surrounding medium. If instead they resulted from a nuclear starburst, the central region would have experienced intense star formation followed by a cascade of supernovae that collectively blew out the bubbles. Either scenario implies that the galactic center underwent a dramatic transformation that affected a substantial fraction of the galaxy. While we are far enough from the center to have been largely unaffected, stars and planetary systems closer to the action would have experienced intense radiation and energetic particle bombardment. Superbubbles on smaller scales are also dangerous features of galactic disks. These structures form when stellar winds and supernovae from OB associations, groups of massive, hot stars born together, combine to blow out enormous cavities in the interstellar medium. These bubbles can grow to hundreds of light-years in diameter and are bounded by dense, expanding shells of compressed gas. The shells eventually fragment and can trigger new star formation, creating a feedback cycle. Inside the bubbles, the gas is hot, thin, and highly ionized, conditions hostile to the formation of new stars or the survival of any existing planetary systems that might find themselves engulfed as the bubble expands. The observation of superbubbles in other galaxies reveals that they are common features in actively star-forming regions. Some galaxies show multiple interconnected superbubbles, creating a Swiss cheese structure in the interstellar medium. The largest superbubbles can even blow out of the galactic disk entirely, creating pathways for gas to escape into the halo. This process, called superbubble breakout, allows material to flow freely between the disk and halo, contributing to the galactic fountain process described earlier. Magnetohydrodynamic processes in galaxies introduce additional layers of complexity and potential danger. The interstellar medium is permeated by magnetic fields that, while weak compared to terrestrial standards, play important roles in the dynamics of gas and cosmic ray propagation. In regions where supernova explosions or stellar winds inject energy, the magnetic fields can be amplified to much higher strengths. These amplified fields can trap cosmic rays, creating regions of space with elevated radiation levels that persist for millions of years after the initial energy injection. Galactic dynamos, the processes by which galaxies generate and maintain their magnetic fields, are still not fully understood, but they clearly involve the interaction of turbulent gas motions with differential rotation. In galaxies with very active star formation or powerful central sources, the magnetic fields can become highly structured and intense. Some active galaxies show evidence of magnetic fields 1,000 times stronger than the Milky Way's field, strong enough to significantly affect the dynamics of the interstellar medium and the propagation of cosmic rays. In such environments, charged particles would spiral along magnetic field lines rather than traveling in straight paths, creating complex patterns of radiation exposure. Now we must consider how galactic environments affect the chemistry available for life. The metallicity of a galaxy, its abundance of elements heavier than helium, determines what types of planets can form. In metal-poor environments such as ancient galaxies or the outer regions of present-day galaxies, planetary systems would be predominantly composed of hydrogen and helium. Rocky planets like Earth require substantial amounts of oxygen, silicon, iron, and other heavy elements, which are only available in metal-rich environments. This means that even if a galaxy is otherwise safe in terms of radiation levels and gravitational stability, low metallicity could prevent the formation of terrestrial planets capable of supporting life. Conversely, regions of exceptionally high metallicity present their own challenges. In the inner regions of large galaxies where metallicity can exceed the solar value by factors of 2 or 3, planetary systems would form with different compositions than our solar system. Planets might be larger and denser due to the greater abundance of heavy elements, potentially leading to super-Earths with surface gravities too strong for complex land-based life to evolve easily. The chemical composition of atmospheres would differ as well, with potentially higher abundances of carbon or nitrogen relative to oxygen, leading to chemistry quite unlike Earth's. The temporal evolution of galactic metallicity introduces another factor. When a star forms within its galaxy's history affects what raw materials are available. Stars that formed 10 billion years ago, early in their galaxy's history, would have much lower metallicity than stars forming today, having only the metals from the first generations of stars available. This creates a cosmic timeline of habitability. Perhaps the first few billion years after galaxy formation produced only metal-poor environments unsuitable for Earth-like planets. Followed by a golden age once sufficient enrichment occurred, potentially followed eventually by an era when star formation declines and opportunities for new habitable worlds diminish. The relationship between stellar populations and habitability extends to stellar types as well. Population 1 stars like the Sun, which are relatively young and metal-rich, represent the best candidates for hosting Earth-like planets. Population 2 stars, which are old and metal-poor, are less promising. Population 3 stars, the hypothetical first generation of stars formed from pristine primordial gas with essentially zero metallicity, could not have hosted rocky planets at all, as the building blocks simply didn't exist. These first stars were likely extremely massive and short-lived, exploding as supernovae after just a few million years and seeding the universe with the first heavy elements, making possible all subsequent generations of stars and planets. Chemical inhomogeneities within galaxies create a patchwork of conditions for planet formation. Even within a single galaxy, metallicity can vary by factors of 2 or more depending on location and local history. Regions that have experienced recent star formation and enrichment from supernova ejecta will have higher metallicities than regions that have been quiet for billions of years. This creates ecological niches within the galaxy, some regions suited for forming Earth-like worlds, others more likely to produce gas giants or ice worlds, and still others too metal-poor for interesting planetary systems. The phenomenon of galactic archaeology uses the chemical compositions of stars to reconstruct their galaxy's history. Each star is a time capsule, its atmosphere preserving the chemical signature of the gas cloud from which it formed. By analyzing stellar spectra in detail, astronomers can determine not just overall metallicity but the abundances of dozens of individual elements. These chemical fingerprints reveal the types of supernovae and stellar processes that enrich the gas, allowing us to piece together the history of star formation, stellar death, and chemical evolution in the galaxy. This archaeological approach has revealed that the Milky Way has a complex history involving mergers with smaller galaxies. Stars from these consumed galaxies can still be identified by their unusual chemical signatures and orbital characteristics. The ongoing absorption of the Sagittarius dwarf elliptical galaxy is adding stars to the Milky Way that have slightly different chemical properties, contributing to the galaxy's chemical diversity. Every merger event changes the chemical landscape of a galaxy, mixing together material with different enrichment histories and creating new opportunities and challenges for planet formation. Looking beyond individual galaxies, the intergalactic medium itself can be hostile. This tenuous gas fills the space between galaxies and is generally extremely hot, millions of degrees, in galaxy clusters due to gravitational heating as the gas fell into the cluster's gravitational potential well. In less dense environments like galaxy groups or cosmic voids, the intergalactic medium is cooler but still harsh by planetary standards. Any rogue planets or star systems cast out from their galaxies would find themselves in this medium, isolated from galactic environments entirely. These intergalactic wanderers would experience a strange existence. Without the protective cocoon of a galaxy's magnetic field and without the ambient radiation from billions of nearby stars, intergalactic space is dark, cold, and intensely lonely. The cosmic microwave background radiation provides a faint glow at microwave frequencies, but otherwise, the environment is as close to perfect emptiness as anything in the universe. For any planets that retained internal heat or had other energy sources, life might theoretically persist, but it would be completely isolated from the galactic ecosystem that gave it birth. The concept of a galaxy being dangerous takes on new meaning when we consider anthropogenic modifications. Advanced civilizations capable of stellar engineering might, whether intentionally or accidentally, make their galaxies more dangerous. A civilization that mastered Dyson sphere construction might systematically harvest energy from every star in its galaxy, dimming it and making it nearly invisible to external observers. If they made mistakes or encountered unforeseen consequences, they might trigger cascading failures, perhaps inducing premature stellar evolution or destabilizing orbits in binary systems. More dramatically, civilizations with access to truly extreme energy sources might engage in activities that reshape their galactic environment. The hypothetical quasar weapon, using a galaxy's central black hole as an energy source for a beam weapon, would turn the galaxy itself into a danger to other galaxies. While this ventures into speculative territory, it reminds us that sufficiently advanced technology could potentially weaponize galactic-scale phenomena. The universe might contain galaxies made dangerous not by natural processes, but by the activities of their inhabitants. On more modest scales, a civilization expanding through its galaxy might render it dangerous through biological or technological contamination. Self-replicating probes spreading through the galaxy could, if improperly programmed, consume resources needed by other life forms or create dead zones inhospitable to biology. Biological contamination, the inadvertent or deliberate spread of microorganisms between star systems, could introduce invasive species to vulnerable ecosystems, potentially causing extinctions. Even information hazards could be dangerous, transmitting detailed instructions for dangerous technologies or containing mimetic content that destabilizes civilizations could make certain regions of a galaxy hazardous to explore or communicate with. These anthropogenic concerns, while speculative, highlight that galaxies exist on timescales spanning billions of years. Most galaxies are young enough that if they ever hosted advanced civilizations, those civilizations might still be active. The absence of obvious signs of galactic-scale engineering in our observations, the so-called Great Silence, could mean such civilizations are rare, hidden, or don't engage in galaxy-spanning activities. Or perhaps we simply haven't recognized the signs yet. Some researchers have speculated that certain unusual astrophysical phenomena might actually be signatures of advanced engineering, though mainstream science generally favors natural explanations. The statistical nature of galactic dangers bears examining. While individual catastrophic events like nearby gamma-ray bursts are rare, over billions of years the cumulative probability becomes significant. A star's journey through its galaxy exposes it to various hazards over time, passing through spiral arms where supernova rates are higher, occasional encounters with molecular clouds or other stars, exposure to cosmic rays from distant sources, and the gradual change in the galaxy's overall properties as it evolves. Life on a planet must survive not just current conditions but the full history and future of hazards it will encounter. This temporal dimension explains why galactic habitable zones are not fixed regions but evolve over cosmic time. The habitable zone in a young, actively forming galaxy might be very different from that in a mature system like the present-day Milky Way. Early on, the entire galaxy might be too violent for stable habitable conditions anywhere. Later, after substantial chemical enrichment but before star formation declines too much, a broad habitable zone might exist. Eventually, as gas is consumed and the galaxy transitions toward quiescence, the habitable zone might contract or disappear entirely as new planet formation ceases and old planets age beyond habitability around their evolving stars. The multimodal nature of galaxy evolution, the fact that galaxies can follow different evolutionary paths depending on their mass, environment, and merger history, creates a diversity of habitability trajectories. Some galaxies might offer long, stable periods suitable for life to arise and evolve. Others might undergo early violent phases that prevent life from gaining a foothold, only to settle into peaceful conditions too late, after their star formation has already ceased. Still others might cycle between active and quiescent phases, with each active period potentially resetting the habitability clock by sterilizing large regions of the galaxy. Ultimately, the concept of dangerous galaxies serves as a lens through which we can examine the full spectrum of galactic phenomena and their implications for life. From blazing quasars to dying ellipticals, from colliding spirals to bizarre irregulars, each type of galaxy creates its own unique set of challenges and opportunities for biology. By understanding these environments, we gain not only scientific knowledge but also perspective on our own cosmic situation. We inhabit a relatively benign galaxy during a relatively calm period in its history, orbiting a stable star in a safe neighborhood. This remarkable circumstance has allowed life on Earth to flourish and intelligence to emerge. Recognizing how special and contingent our situation is deepens our appreciation for the universe's diversity and complexity, and perhaps motivates us to preserve and protect the rare and precious phenomenon of life wherever it occurs in this vast and often dangerous cosmos. The phenomenon of galactic winds driven by supermassive black hole feedback represents one of the most powerful forces capable of reshaping entire galaxies. These winds can reach velocities exceeding 10,000 kilometers per second, carrying away gas that might otherwise form new generations of stars. The energy required to accelerate such enormous quantities of material comes from the accretion disk surrounding the black hole, where gravitational potential energy is converted into kinetic energy with remarkable efficiency. These outflows can extend for hundreds of thousands of light years, far beyond the visible boundaries of the host galaxy, creating vast cavities in the surrounding intergalactic medium. What makes these winds particularly dangerous is their ability to quench star formation across an entire galaxy almost instantaneously on cosmic timescales. A galaxy experiencing such feedback transitions from a vibrant, star-forming system to a sterile environment within just a few million years, the blink of an eye in galactic terms. Any emerging biospheres within such a galaxy would find their long-term prospects suddenly and dramatically curtailed. The raw materials necessary for future planetary systems would be expelled into intergalactic space, and existing systems would experience dramatically increased radiation levels as the wind material glows from its violent acceleration. Observations of these winds reveal complex, multi-phase structures. The fastest components consist of highly ionized atoms stripped of most of their electrons by the intense radiation field, while slower, cooler components contain molecular gas and dust. The interaction between these different phases creates turbulence and shocks that heat the gas further and produce additional radiation. In some cases, the wind material collides with dense clouds in the galaxy's disk or halo, compressing them and potentially triggering localized bursts of star formation even as the overall galaxy is being stripped of its gas supply. This creates a paradoxical situation where the same process that kills star formation on galactic scales might briefly stimulate it in specific locations. The X-ray binary population within a galaxy introduces another layer of danger that affects local rather than galactic scales. These systems consist of a neutron star or stellar mass black hole accreting material from a companion star, typically a massive star that is overflowing its Roche lobe or producing strong stellar winds. The accretion process produces intense X-ray emission as material spirals inward and heats to temperatures of millions of degrees. X-ray binaries are among the brightest X-ray sources in galaxies, and their X-ray luminosities can exceed the total optical output of their host stars by factors of thousands. For any planetary system located within a few dozen light-years of an X-ray binary, the radiation environment would be extraordinarily hostile. X-rays penetrate deeply into planetary atmospheres, ionizing molecules and creating cascades of secondary particles. Unlike ultraviolet radiation, which is absorbed in the upper atmosphere, X-rays reach much deeper, potentially affecting even ground-level conditions. The X-ray flux from a nearby binary would fluctuate as the accretion rate varies, creating an unstable radiation environment. During outbursts, when the accretion rate suddenly increases, X-ray luminosities can spike by factors of thousands or millions, briefly transforming a moderately dangerous neighbor into a lethal one. Ultraluminous X-ray sources, or ULXs, push this danger to extremes. These objects emit X-rays at luminosities that exceed what should be possible for stellar mass black holes accreting at their theoretical maximum rates. Their nature has been debated for decades, with explanations ranging from intermediate mass black holes to stellar mass compact objects accreting at super-Eddington rates through special geometric configurations. Recent observations have identified some ULXs as extremely magnetized neutron stars, magnetars, accreting from massive companion stars. Regardless of their exact nature, ULXs represent exceptionally powerful sources of high-energy radiation that would pose severe threats to any life forms within their vicinity. The concept of dynamical heating in galaxy cores deserves deeper examination. As stars orbit within the dense central regions of galaxies, they occasionally pass close to each other, exchanging energy through gravitational interactions. These encounters cause the stellar velocity distribution to evolve over time, typically resulting in the core heating up, stars acquiring higher random velocities, while the outer regions may cool slightly as energy is transported outward. This process can create a core halo structure where the central region has much higher velocity dispersions than the surroundings. In cores that have experienced substantial dynamical heating, stellar orbits become increasingly chaotic and unpredictable. The high velocity dispersion means that stars move on complex paths rather than simple, regular orbits. For planets orbiting these stars, the varying gravitational environment creates long-term instabilities. While the time scales involved are typically millions or billions of years, long enough that individual planetary orbits remain stable on human timescales, the cumulative effect over the age of a galaxy can be significant. Planetary systems might gradually become destabilized, with outer planets being perturbed into eccentric orbits or ejected entirely, leaving only the innermost worlds in stable configurations. Gravitational microlensing events provide another mechanism through which we can detect dangers lurking within galaxies. When a massive object passes between a distant star and an observer, its gravitational field acts as a lens, briefly magnifying the star's light. By monitoring millions of stars for these rare events, astronomers have discovered numerous free-floating planets, worlds that orbit no star but instead drift through interstellar space. These rogue planets were likely ejected from their original planetary systems through gravitational interactions, perhaps during the chaotic early phases of system formation or through later perturbations from passing stars. The discovery that galaxies may contain billions of rogue planets, possibly outnumbering planets in stable orbits, suggests that planetary ejection is a common process. This implies that many regions of galaxies experience gravitational disturbances severe enough to disrupt planetary systems. Some of these ejections might occur during galactic mergers, when close encounters between stars become more frequent. Others might result from the decay of unstable multi-planet systems over billions of years. Each rogue planet represents a failed biosphere, a world that might have harbored life but was cast into the frozen darkness of interstellar space before biological processes could develop or mature. Thorn-Zitko objects represent one of the most bizarre stellar configurations imaginable and exemplify the extreme astrophysics possible in dense galactic cores. These hypothetical objects would form if a neutron star were somehow captured into the interior of a red giant or supergiant star. The neutron star would sink to the center of the giant through dynamical friction, where it would accrete material from the giant's interior at prodigious rates. The energy released by this accretion would power the giant from within, creating a star whose energy source is fundamentally different from normal stellar fusion. If Thorn-Zitko objects exist, and there are a few candidates that might fit the description, they would be extraordinarily dangerous in their vicinity. The accretion onto the central neutron star would produce intense X-rays and gamma rays, though much of this radiation might be absorbed by the giant's outer layers. More significantly, these objects might be precursors to unusual supernova explosions with properties different from standard core collapse events. The exact fate of a Thorn-Zitko object remains uncertain, but it might eventually explode after the giant's envelope is exhausted, potentially producing an energetic transient with unusual chemical signatures. The process of stellar collisions in dense environments produces a menagerie of exotic objects. In globular clusters and nuclear star clusters where stellar densities are extreme, direct collisions between stars occur frequently enough to be astronomically significant. These collisions can produce blue stragglers, stars that appear younger and bluer than they should be given the age of the cluster. They can also create highly magnetic stars, rapidly rotating stars, and even runaway mergers where multiple collisions produce increasingly massive objects that might eventually collapse into black holes. Each collision is a violent event despite the relatively gentle term, collision, used to describe it. When two stars merge, their combined energy heats the merger product to extreme temperatures, and the rapid mass loss during the collision can create expanding shells of hot gas. Any planets orbiting either of the pre-collision stars would certainly be destroyed, either vaporized by the heat or gravitationally disrupted by the chaotic mass distribution of the merging stars. The post-merger object might briefly shine with extraordinary luminosity as it settles into a new equilibrium, bathing the surrounding region in intense radiation. Globular clusters themselves, while not galaxies, share certain dangerous characteristics with galactic cores due to their high stellar densities. These ancient spherical collections of stars orbit galaxies like satellites, and some contain hundreds of thousands, or even millions of stars packed into volumes just tens of light years across. The densest regions of globular clusters approach or exceed the stellar density of galactic nuclei, creating environments where gravitational interactions dominate the dynamics. Three-body encounters, situations where three stars pass close together simultaneously, can eject one star at high velocity while binding the other two more tightly, a process that gradually evaporates the cluster over time while creating a population of high-velocity escapees. For any hypothetical planets in globular clusters, life would face extraordinary challenges. The high stellar density means frequent close passages by other stars, which would perturb the Oort cloud and potentially send comet showers toward the inner system. The cluster's low metallicity. Globular clusters are ancient and formed before significant chemical enrichment, means that rocky planets would be rare and likely smaller than Earth. The intense stellar crowding would create a night sky unlike anything experienced on Earth, with thousands of bright stars visible and providing significant illumination even during nighttime. This might sound beautiful, but the radiation from so many nearby stars could be problematic for maintaining stable atmospheric chemistry. The tidal radius of a galaxy, the distance beyond which objects are more strongly attracted to external gravitational sources than to the galaxy itself, defines a boundary of sorts for galactic influence. Beyond this radius, globular clusters, dwarf galaxies, and stray stars can be pulled away by the gravitational field of a neighboring galaxy or the overall cluster potential if the galaxy resides in a rich cluster. This creates a region of space where allegiances are uncertain, where objects might transition from being part of one galaxy to being part of another or becoming intergalactic wanderers. Stars and clusters near the tidal radius experience time-varying gravitational fields as they orbit and as the galaxy moves through its environment. This creates additional instabilities beyond those experienced in the stable interior regions. Over time, the tidal forces preferentially remove objects from the outer parts of galaxies, causing them to shrink unless they can acquire new material from their surroundings. This process has reshaped countless dwarf galaxies and continues to modify galactic structure on the longest timescales. The intracluster light in galaxy clusters, diffuse glow not associated with any particular galaxy, tells a story of violent redistribution of stars. This light comes from stars that were stripped from galaxies during interactions and now orbit independently within the cluster's gravitational potential. The process that creates intracluster light is traumatic for the galaxies involved, with tidal forces literally tearing stars from their homes and scattering them into the space between galaxies. Some estimates suggest that up to half of all stars in rich galaxy clusters might eventually end up as part of the intracluster light rather than belonging to any particular galaxy. Stars that find themselves contributing to intracluster light have been fundamentally displaced from their original environments. They orbit within the cluster potential on timescales of billions of years, occasionally passing through or near galaxies but never remaining bound to any. For any planets around these stars, the experience would be profoundly disorienting across evolutionary timescales. The night sky would transform as the star's trajectory took it through different regions of the cluster, sometimes near galaxy cores where the stellar density is high, sometimes in the sparse regions between galaxies where isolation dominates. Intermediate velocity clouds in the Milky Way's halo represent another mysterious and potentially significant phenomenon. These are clouds of neutral hydrogen moving at velocities that are high but not as extreme as high-velocity clouds. Their origins are debated, with possibilities including material expelled from the galactic disk by supernova-driven fountains, remnants of ancient satellite galaxies, or gas falling into the galaxy from the intergalactic medium. Some intermediate velocity clouds show signs of interaction with the galactic disk, suggesting they may eventually rain down and contribute to future star formation. When these clouds collide with the galactic disk, they can trigger localized bursts of star formation through the compression of existing disk gas. The collision creates shockwaves that propagate through both the cloud and the disk material, heating and compressing the gas. Over millions of years, this compressed gas fragments and forms new stars. The process injects fresh material into the disk, potentially extending the galaxy's star-forming lifetime, but it also creates regions of active star formation that, as we've discussed, can be hazardous due to the resulting supernovae and stellar radiation. High-velocity clouds, moving at even greater speeds, pose more dramatic potential impacts. Some of these clouds are falling into the Milky Way from the intergalactic medium at velocities exceeding 200 km per second relative to the disk. When they strike the disk, the collisions are violent, creating expanding shells of shocked gas and potentially triggering intense star formation. The Smith Cloud, one of the most studied high-velocity clouds, is predicted to collide with the Milky Way's disk within 30 million years, soon by cosmic standards. The collision will create a burst of star formation visible as a bright complex in future astronomers' telescopes, but it will also inject considerable energy into the disk and potentially disrupt existing structures. The formation scenarios for high-velocity clouds remain contentious, with some possibly being primordial material that never fell into the galaxy during its initial formation. Others being tidal debris from satellite galaxies, and still others potentially being material expelled from the galaxy that is now falling back. Regardless of their origin, their presence and eventual impacts demonstrate that galaxies are not closed systems but continue to exchange material with their surroundings throughout their lifetimes. This ongoing accretion and ejection modifies galactic properties and creates intermittent hazards for regions where infalling material strikes the disk. Wormholes, while remaining purely theoretical and possibly prohibited by the laws of physics, deserve mention in any comprehensive discussion of galactic dangers. If traversable wormholes could exist and if some advanced civilization discovered how to create or stabilize them, galaxies containing such structures might become extremely dangerous in unexpected ways. A wormhole connecting two distant parts of a galaxy or linking to another galaxy entirely would allow rapid transit and communication across distances that normally require millions of years to traverse even at light speed. The gravitational effects of wormholes might be severe in their immediate vicinity. The exotic matter required to hold a wormhole open, matter with negative energy density that violates various energy conditions, could have strange gravitational effects. Additionally, instabilities in wormhole structures might cause them to collapse catastrophically, potentially creating significant disruptions in space-time. If wormholes could somehow connect regions of space-time with different properties, different expansion rates, different vacuum states, or different physical constants, the consequences of opening such a connection would be unpredictable and potentially catastrophic. From a more practical standpoint, any galaxy containing an active wormhole network would face dangers from information and travel. Diseases, invasive species, dangerous ideas, or hostile actors could spread through the galaxy much more rapidly than the natural speed limit imposed by light. This could create synchronized crises where problems emerge simultaneously across vast regions rather than allowing the natural quarantine provided by interstellar distances. The galaxy would become, in effect, much smaller and more connected, with all the vulnerabilities that increased connectivity entails. Vacuum decay represents perhaps the ultimate galactic, and indeed universal, danger, though it remains highly speculative. Some theories suggest that the vacuum of space might not be in its lowest energy state but rather in a metastable false vacuum. If this is true, quantum fluctuations could potentially trigger a transition to the true vacuum state. This transition would propagate outward at the speed of light as an expanding bubble, and inside the bubble, the laws of physics might be different, particles might have different masses, forces might have different strengths, and atomic nuclei might not be stable. If vacuum decay occurred anywhere in a galaxy, that galaxy would be doomed, though its destruction would proceed at a predictable rate, the speed of light. Stars, planets, and any civilizations on the side of the galaxy where the decay originated would be destroyed first, with a wave of annihilation spreading outward. Observers on the opposite side of the galaxy might have millions of years of warning as they watch distant regions wink out, but there would be no escape. The bubble would eventually encompass the entire galaxy and continue expanding to consume the observable universe. Fortunately, the stability of our vacuum over the age of the universe suggests that if we are in a false vacuum, it is extraordinarily stable, with decay rates so low that the expected time to the next transition vastly exceeds the current age of the universe. Dark matter annihilation in galactic centers could create another exotic source of danger. If dark matter consists of certain types of weakly interacting massive particles that are their own antiparticles, then collisions between dark matter particles would result in annihilation, producing standard model particles including high-energy gamma rays and other radiation. The dense dark matter concentration in galactic centers would be the primary sites for such annihilation, potentially creating excess gamma-ray emission from the galactic core. Searches for this annihilation signal have produced intriguing hints but no definitive detection. The Milky Way's galactic center does show an excess of gamma rays at certain energies that could potentially be explained by dark matter annihilation, though alternative explanations involving unresolved populations of pulsars or other astrophysical sources remain viable. If dark matter annihilation does occur at significant rates, the galactic center would be bathed in high-energy radiation beyond what we'd expect from conventional sources, adding another hazard to an already dangerous region. Galactic cosmic rays, high-energy particles that pervade the galaxy, constitute a persistent, diffuse threat to life throughout the galactic disk. These particles, mostly protons and atomic nuclei accelerated to relativistic speeds by supernova shocks and other energetic processes, constantly bombard planetary systems. Earth's magnetic field and atmosphere provide substantial protection, but planets lacking these defenses would be directly exposed to cosmic ray flux. The radiation dose from galactic cosmic rays would make surface life challenging on planets without protective magnetic fields or thick atmospheres. The cosmic ray spectrum extends to extraordinary energies, with some particles carrying as much kinetic energy as a baseball thrown at highway speeds concentrated in a single atomic nucleus. These ultra-high-energy cosmic rays, with energies exceeding 10 to 20 electron volts, are rare but spectacular. Their origin remains mysterious. Supernova shocks seem insufficient to accelerate particles to such extreme energies, leading to speculation about more exotic sources such as active galactic nuclei or even the decay of super-heavy relic particles from the early universe. When these particles strike Earth's atmosphere, they create extensive air showers involving trillions of secondary particles cascading down to the surface. In regions of galaxies with high supernova rates or near powerful cosmic ray accelerators, the background cosmic ray flux would be elevated far above what Earth experiences. This would make maintaining complex biological systems more difficult, as the increased radiation would cause more frequent mutations and cellular damage. Life could potentially adapt to such conditions. Indeed, some extremophile organisms on Earth thrive in high radiation environments, but the evolutionary paths and resulting biospheres might be quite different from those in calmer regions. Supernova remnants themselves remain dangerous long after the initial explosion. These expanding shells of hot gas continue to emit X-rays and accelerate cosmic rays for tens of thousands of years after the supernova event. Young supernova remnants are particularly bright X-ray sources, and their expanding blast waves continue to shock and heat interstellar gas they encounter. A planetary system that happens to be in the path of an expanding supernova remnant would experience steadily increasing radiation levels and cosmic ray flux over thousands of years as the remnant approaches and eventually engulfs the system. The interaction between supernova remnants and molecular clouds creates spectacular structures visible in radio and X-ray wavelengths. When the blast wave strikes a dense cloud, it can't easily penetrate, so it flows around the cloud while sending shock waves into it. These shocks compress the cloud and can trigger star formation, but they also illuminate the cloud in X-rays and radio emission. Systems forming in such compressed clouds would be born into an already hazardous environment, immediately exposed to enhanced radiation from the remnant. Asymmetric supernova explosions introduce another danger through the kicks they impart to neutron stars. When a massive star explodes as a supernova, asymmetries in the explosion can cause the resulting neutron star to recoil at velocities of hundreds of kilometers per second. These high-velocity neutron stars, sometimes called runaway pulsars, streak through the galaxy on trajectories that don't follow the orderly orbital motions of normal stars. They leave behind bow shocks, regions where their motion through the interstellar medium creates shock waves that can be detected in X-rays and radio wavelengths. A runaway neutron star passing through a region of space creates a temporary zone of enhanced radiation and disturbed interstellar medium. If one passed within a few light years of a planetary system, the effects could be significant depending on whether the neutron star is an active pulsar. Young pulsars emit intense beams of radiation from their magnetic poles, and if a system happened to lie in the path of one of these beams, it would be exposed to regular pulses of high-energy radiation. While brief, these exposures would accumulate over the time the pulsar remained nearby, potentially affecting atmospheric chemistry and surface conditions. The eventual fate of neutron stars includes several potentially dangerous scenarios. If a neutron star has a companion star and accretes enough mass from it, the neutron star might exceed the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can support, and collapse into a black hole. This transition would be accompanied by a burst of energy, though likely less dramatic than the original supernova. Alternatively, two neutron stars in a binary system will gradually spiral together as they lose energy to gravitational radiation, eventually merging in a kilonova explosion that produces intense gamma-ray emission and creates heavy elements through rapid neutron capture processes. Kilonovae have only recently been recognized as a distinct class of cosmic explosions, first definitively observed in 2017 when LIGO detected gravitational waves from a neutron star merger and telescopes worldwide observed the electromagnetic counterpart. These events are thought to be the primary production sites for the heaviest elements in the periodic table, including gold, platinum, and uranium. The radioactive decay of these newly synthesized heavy elements powers the kilonova's optical glow, making it shine for days or weeks after the merger. The gamma-ray emission, while less intense than a gamma-ray burst, would still be lethal to life on nearby planets if the beam happened to point in their direction. The distribution of neutron star mergers throughout galaxies and across cosmic time affects the chemical evolution and potentially the habitability of different regions. Galaxies with higher merger rates would have enhanced abundances of heavy R-process elements, potentially affecting the composition of planets forming in those regions. However, these same galaxies would also experience more frequent kilonova events, creating intermittent radiation hazards. There might be an optimal merger rate, high enough to provide substantial heavy element enrichment, but low enough that the radiation hazards remain tolerable over the billions of years required for complex life to evolve. White dwarf supernovae, or type I supernovae, present different dangers than core collapse events. These explosions occur when a white dwarf in a binary system accretes material from its companion until it approaches the Chandrasekhar limit, about 1.4 solar masses, at which point carbon fusion ignites throughout the white dwarf essentially simultaneously. The star doesn't collapse. Instead, the fusion reactions propagate through the star in a matter of seconds, completely disrupting it and leaving no remnant. The explosion is extraordinarily bright, briefly outshining its entire host galaxy, and the energy release is remarkably consistent from one type I supernova to another, making these events valuable as cosmic distance indicators. From a habitability perspective, type I supernovae are particularly insidious because they can occur in old stellar populations where life might have had time to evolve. Core collapse supernovae require massive stars that live only millions of years, so they typically occur in actively star-forming regions where planet formation might still be ongoing and complex life has had little time to develop. But type I events can occur billions of years after the progenitor white dwarf formed, potentially destroying biospheres that have had eons to develop. The binary star systems that produce Type I supernovae are not obviously dangerous until the final rapid accretion phase, giving little warning of impending catastrophe. Nova explosions, while much less energetic than supernovae, occur more frequently and represent another hazard from white dwarf binary systems. In a nova, a white dwarf accretes material from a companion, and when sufficient hydrogen accumulates on the white dwarf's surface, it undergoes explosive fusion. This blows off the accumulated material in a shell that expands outward at thousands of kilometers per second, and the system briefly brightens by factors of thousands or more. Unlike supernovae, novae don't destroy the white dwarf, so the system can potentially experience multiple nova explosions separated by decades, centuries, or millennia depending on the accretion rate. Recurrent novae, systems that have been observed to undergo multiple nova outbursts, demonstrate that some white dwarf binaries repeatedly experience these explosions. Each outburst injects energy and enriched material into the surrounding interstellar medium and poses a radiation hazard to nearby systems. A planetary system orbiting at a distance of several hundred AU from a recurrent nova would experience varying radiation levels as the nova cycles between quiescence and outbursts, creating a periodically hostile environment. Life in such a system would need to cope with these cycles, perhaps by having organisms capable of entering dormant states during the highest radiation phases. Symbiotic stars represent another class of interacting binaries where a white dwarf accretes from a red giant companion. The complex interaction between the white dwarf's hot surface and intense radiation field and the red giant's cool, extended atmosphere creates unusual spectra and variable behavior. Some symbiotic stars undergo nova-like outbursts, while others show more complex variability patterns. The red giant in these systems is often losing mass at high rates through stellar winds, and the white dwarf captures only a fraction of this material, with the rest expanding outward and potentially affecting nearby objects. The accumulated effects of living in a galaxy filled with these various types of transient phenomena, supernovae, novae, kilonovae, gamma-ray bursts, stellar flares, and more, create a kind of cosmic weather that any long-lived civilization must endure. Just as terrestrial life must cope with weather patterns, seasonal variations, and occasional extreme events like hurricanes or earthquakes, galactic civilizations would need to survive the vicissitudes of their cosmic environment. The frequency and severity of these events vary by galactic location and type, creating some regions that are relatively calm and others that are storm-tossed. Statistical studies of supernova rates in different types of galaxies reveal patterns that inform our understanding of galactic habitability. Spiral galaxies with ongoing star formation host both core collapse and Type I supernovae, with the core collapse rate depending on the current star formation rate and the Type I rate depending on the age and metallicity of the stellar population. Elliptical galaxies with little or no star formation host primarily Type I events from their aging stellar populations. Irregular galaxies with bursty star formation can experience periods of high supernova rates followed by quiet intervals. The Milky Way's supernova rate is estimated at roughly 2 per century averaged over long timescales, though the actual rate varies with time as star formation rates fluctuate and as the distribution of stellar ages shifts. Historical records provide direct observations of only a handful of galactic supernovae. The events of 1054, 1572, and 1604 are the most famous, producing the Crab Nebula, Tycho's supernova, and Kepler's supernova respectively. The absence of nearby, bright supernovae since then is somewhat unusual statistically, leading to speculation that we might be overdue for another galactic supernova that would be visible to the naked eye. When the next nearby supernova occurs in the Milky Way, it will provide unprecedented opportunities for scientific observation with modern instruments, but depending on its distance and type, it could also pose measurable risks to Earth. A supernova within a few tens of light years would likely affect Earth's atmosphere through cosmic ray and gamma-ray exposure, though such close events are extremely rare. More distant events within a few thousand light years would be spectacular visual displays, potentially brighter than Venus and visible during daytime, but would pose minimal direct threats. The closest supernova candidates, such as Betelgeuse or Eta Carinae, are far enough away that their eventual explosions will be magnificent but not dangerous to Earth's biosphere. This exploration of dangerous galaxies and their internal hazards reveals a cosmos that is simultaneously creative and destructive, where the same processes that enable the formation of stars, planets, and life also generate threats to their continued existence. The universe operates on scales of time, space, and energy that dwarf human experience, yet through science, we can comprehend these vast phenomena and our place within them. Every galaxy, from the most violent quasar to the quietest dwarf elliptical, tells a story written in the language of physics, and learning to read these stories expands our understanding of the cosmic environment that has given rise to consciousness and allows us to contemplate our own existence and fate among the stars.